Hello everyone. In this video, I am going to show you Chapter 4, Section 4.1, Moment of a Force, Scalar Formulation, Section 4.2, Cross Product, Section 4.3, Moment of a Force, Vector Formulation, and also Section 4.4, Principles of Moments. We'll start with looking at the definition of a moment. The moment of a force about a point provide a measure of the tendency for rotation, sometimes called a torque. Notice that the word that we're using here says tendency, meaning sometimes you don't actually need to rotate the object as long as it's trying to rotate. It has a moment in there. In the 2D case, magnitude of the moment is defined as m equals force times distance, and that's shown in in this diagram. D is the perpendicular distance from point O, which is the axis of rotation, to the line of action of the force. And in 2D, the direction of m is either clockwise or counterclockwise, depends on which direction it's trying to rotate. And also, by definition, we have counterclockwise, it's always defined as positive, and clockwise defined as negative. This is similar to in the xy coordinate. X on the x direction, positive is always going to the right, negative going to the left. On the y direction, positive going up and negative coming down. So for when we talk about moment, going back to the slide, when we talk about moment, counterclockwise is always considered positive and clockwise is considered negative. So let's take a look at this example right here. I have a force acting on this object. Okay, so this thing right here, I can break my force into two different directions. I can break the force into the vertical component and the horizontal component, where axis rotation is right here about point O. I'm trying to rotate about point O. And you notice that these two forces, when I break it along the horizontal direction and the vertical direction, they are trying to rotate about point O, one of them clockwise, with the other one counterclockwise. What I'm saying, what I'm trying to show you is that, so point of rotation is right here. If you follow the direction of the vertical component of the F, follow the direction of that the vertical component direction. Vertical goes up, meaning about point O. Vertical component is trying to rotate about point O. This is going to be counterclockwise. And then the horizontal one, let me use a different color. The horizontal one, it's still point O is right here, axis rotation right here in the middle. That horizontal component follow the direction about that point O. Sorry, my sketch is kind of ugly. About that point O, it's totally opposite direction of that green one. And the red one right here is clockwise. Okay, so this problem here is trying to say, hey, one of them is clockwise and one of them is counterclockwise. That's why the force times the perpendicular distance right here, Fy component times A, y component times A is counterclockwise. The green one generating a positive moment. In the red one, Fx multiplied by the perpendicular distance B, which is generating a negative because it's clockwise. Hope that helps you. So this defines the magnitude, and they also be careful with the sign. Counterclockwise positive and clockwise negative. So in the 2D case, it's pretty straightforward when you know the perpendicular distance. If you do know the perpendicular distance, multiply the force by the perpendicular distance, we can find out the magnitude of the moment. Now, a more general approach to find the moment of a force will be using the cross product. This is very useful when you're seeing problems in 3D. I will show you some examples in a little bit, but by definition, let's talk about what is cross product. So let's say C equals A cross B. It looks very much just like a multiply sign, but in our vector notation, so C, this over here, that cross in between the A and the B stands for cross product. I want to do A cross B. The magnitude and excuse me, magnitude and direction of the resultant vector can be written as A cross B, which will be AB sine theta UC. where UC is a unit vector perpendicular to A and B vector, or to the plane that is containing vector A and vector B. Using the right-hand rule is very useful. It's very useful to determine the direction of that vector resulting from a cross product. For example, I cross j will equal to k, looking at this diagram. Notice that cross product is different than the dot product in the last few videos that we talk about dot product. Cross product, when I cross I, J cross J, K cross K cross K, anything that you do a cross product to itself, it will be zero. One more time, know that a vector crossed into itself is going to be a zero. This is totally opposite than the dot product. Only if I have I cross J gives you K, J cross K gives you I, etc. So also, cross product can be written as a determinant in linear algebra, right? We can look for the determinant of this 3 by 3 matrix to find a cross product. So I have A cross B. You write your IJK on the top and put your components of your A vector on the second row, components of your B vector on the third row. For the I element, we're going to get rid of the column and the row that contains the column and the row that contains the I. Okay, so you're left by the 2 by 2, and then using that 2 by 2, you're going to go from left to right. Okay, AY BZ, multiply that together, subtract minus AZ times BY. So that's your I component. And then similarly for your J component, you're going to get rid of the row and column that contains the J, and then you're looking at this AX diagonally, AX multiplied by BZ minus AZ times BX. And then notice that the second term in front of it will be a negative. And really what happens is, you have positive, negative, positive. If you have a fourth term, the fourth term will be negative as well down here. If there's like a fourth term, but we don't have one, just so you know, it alters between your positive and your negative. And then the K component, similarly, we're going to get rid of the row and the column that contains the K component. And then over here, we're going to do the cross and subtract AX BY minus AY BX. Okay, and the last term over here is going to be a positive term. In the 3D case, moment can be calculated using this 2D scalar approach, but it's very time consuming. It's actually very lots of projection you got to work with, etc. So in the 3D cases, it actually makes better sense when you're using a vector cross product. And R over here, moment equals R cross F, not multiply, R cross F. R is the position vector from point O to any point on the line of action of the F. So similarly, we talk about this equation when we talk about the A and the B. So you're using this equation. So we have the IJK component. First one positive, it's not written, but it's an invisible positive there. Second term will always be negative in front of that J. And then last one will be the plus. And be careful with what subtract what. And then where that comes from, I talk about it in the previous slide. The unit here, be careful, units are always going to be Newton meter or pound foot. Let's take a look at an example. This one's only in 2D, so we are going to look at 2D, 2D, the scalar way for this problem. So first thing is that force is at an angle. I am going to break down that force into horizontal component and vertical component. So I go here and here, okay? Horizontal component, it's going to be 4/5 multiplied by the hypotenuse, which is 100. If you need help with that, please let me know. So this go back to the trig function that we've been talking about in the past several sections. And then the vertical component is going to be 3/5 times multiplied by 100. Again, if you wonder where that comes from, please stop by on my Friday sessions, and I will be happy to help you out further. And then so these two components, the horizontal one, let's say the horizontal one, 4/5 times 100 is trying to rotate, my axis rotations right here, is trying to rotate about the O. This is going to be clockwise, which will be a negative value, negative torque. And let me use a different color for the y component. Y component is coming down this way, okay? This one right here looks like it's trying to rotate about zero point 0, same thing, clockwise, and it will be a negative value. Let's take a look. So force over here is already a negative value because see horizontally x is going to the right, positive, but vertically it's coming down, so negative value. So it's negative. That sorry, I did not label it over here, but this one is positive, that one is negative because I'm going down in the vertical direction. Now, over here, I was using the scalar way. So really, all you gotta know is that both for both of them, either the horizontal or the vertical component of the forces is trying to rotate it clockwise, meaning both of them are negative. So that's why you have a negative sign here, negative sign here. So the 100 times 3 over 5, that is the y component. Y component, we're looking at the, what is it called? Perpendicular distance will be a 5 meter. So this is the perpendicular distance from the point of rotation to the y component, to the horizontal perpendicular distance to the line of action of the force on the vertical direction. And then similarly, this 2 meter is the perpendicular distance. See, over here is 2 meter, meaning over here is 2 meter, right? Same thing is the purpose. So the 2 meter is going to be the perpendicular distance from the axis of rotation to the line of action of the force on the horizontal direction. So putting these two together, we got negative 460 Newton meter, or we call it 460 Newton meter clockwise if you don't write that negative sign. Example number 2 says I have force number 1 F1 and force number 2 F2. This is a 3D case. We want to find the resultant moment by the force about 0.0. 0.0 is down here. In this problem, you see it's slightly more complicated is because it's going to the 3D. So it makes more sense that we are going to use the cross product method of cross product. So F1, F2, that's first put F1 and F2 together. We can put, since they have all their components already, we can put them together by combining the I component together, the J component together. Be careful, the sign needs to go together, right? And then you have K, I, and IJ, and then the K component together. Okay, combine that F1 and F2 together, I have a resultant force that includes F1 and F2. And then next thing is looking for the position factor. Position factor OA, remember we talk about you need the coordinate. So OA, for O, your coordinate is 0, 0, 0 because it's at the origin. For your B, your coordinate X value is going to be 5 feet. And then your Y value, sorry, X value is 4, my bad. X value is 4 feet because it's this way. It's this one right here. And then your Y value it's this one right here, which is 5 feet. And then the Z value is going to be 3. Sorry, let's write it again. It will be 4, 5, 3. And then you subtract ending point minus the starting point. Since the starting point is going to be the 0, 0, 0, so that means the position factor, position factor will be 4 on the I, 5 on the J, and then 3 on the K. Okay, so that's where that 4, 5, 3 comes from. And then you put it into this 3 by 3 matrix and looking for the determinant. And we talk about you need your I component, you need your J component, and your K component. The second one is negative. Look, there's a negative sign right here. And then really you're going to follow the what is it called, the equation or the formula, this one right here or this one right here. It's the same thing, but this slide tells you what's going on, where that comes from. But if you want to just use the formula, which will be this one, okay, you're going to do what I would just talk about. For example, the I, when you're looking for the I component, the very first one up until here, this portions of it, you are going to eliminate the row and column that includes I and looking for the determinant. So you have 5 times 175 minus 3 times 130. That's where that box comes from. That's your I component. And you do similar for the J and for the K. And remember the J component at the beginning, the sign needs to be negative. Okay. Group problem 2D case, again, for this hammer, we can try to pick up this nail. We can use the scalar way where I break the force into the vertical and horizontal component. Now, in this case, our horizontal and vertical is sort of at an angle. So this one is going to be the horizontal one is going to be 20, which is F, right, 20 cosine 30 degree. And then the other one over here is going to be 20 sine 30. Okay, so over here, so what it's saying is that, okay, that 20 cosine 30 component, the perpendicular distance is going to be this much, which is 18 inches. And then that vertical component, 20 sine 30, your perpendicular distance is going to be this much, 5 inches. Okay, so be careful which one is clockwise, which one's counterclockwise. If you have a hard time telling, just, your axis of rotation is right here. Follow the direction of that arrow. Okay, this one goes this way, which means this is going to be a clockwise negative. In the other one, let me use color purple. This one right here, right? So I am vertical one. Follow the direction of that. Rotating about this point, the cross, where the cross is. So we go this way, meaning this is going to be clockwise as well, negative. Okay, so both of them clockwise. Okay, so here is our breakdown for our forces. Sine 30 for the y component, 20 cosine 30 for the x component. And it's negative here. It's also negative here because both forces is trying to rotate about that support point A. It's trying to rotate it about that point clockwise. So that's why both of them is negative, and we can put them together. Next one is another 3D problem. Again, when the problem gets complicated, we are going to use cross product, method of cross product. We have our F over here. We got the two angles projected the first time into the XY plane. You have a 30-degree angle. And then in between that, that will project it, and you can project it again into the Y axis being a 40-degree angle. So if you need help with this, where all this sine cosine comes from, please let me know. Please stop by my Friday tutorial, Friday Q&A session. I will be happy to help you out. So over here, this step right here, we talk about it. We do a lot of problems in this in chapter 3. Okay, so I'm not gonna break it again for you. I'm assuming you understand where that comes from. But again, if you need help, please let me know. I will be happy to help you. Next thing is that once we get the F IJK component, we're going to need to look for the position factor AC. And again, we're looking for the A is at the origin 0, 0, 0, and we're looking for the coordinate for your C. And then you have your ending point, subtract the ending point, subtract the starting point. So if you need help right here, your X component on the X direction, it will be that this portion plus this portion. So it will be 250 plus 300, which will be 550. Okay, so that is the X. That is how much you have on the X. And notice that over here they put 0.55. That's because the unit here, 550, is in millimeter. So we're going to convert it into 0.55 meters. The Y component is going to be this much, this portion, which is 400. And again, when we convert it to meter, it becomes 0.4. And then the Z component, since it's going down, the Z component, since it's going down, we have this portion of that Z component, which will be negative 200. It's coming down, okay? And over here, it's negative 0.2, meaning we'll convert it into meter. Now putting into the matrix form, the first row gives you IJK. Second row is going to be the position factor, 0.55, 0.4, negative 0.2. And then the last row here is the components of the force factor. We put them together. And then you are going to do the cross product or finding the determinant of this 3 by 3. That gives us the final result of the vector A. Okay, this is all I want to show you in this video. Please let me know if any questions, and I look forward to see you in our Friday Q&A sessions if you have any questions further. Thank you for watching.